Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series. I hope all of you are doing well and studying with me regularly, okay? So as you all know, we have started a series where we are going to cover each and every concept that is going to be asked in your KCET Chemistry examination, and simultaneously we are going to solve all the PYQs and practice a lot of questions, right? So yes, in today's video we are going to cover the part 3 of the most important topic, that is solutions. So today we'll be covering two important topics, that is colligative properties and abnormal molar mass. So please remember, 60% of questions from this chapter comes from these two topics. So it is very important that you master colligative properties and abnormal mass at any cost if you are an aspirant of KCET 2025 chemistry examination. Okay, so yes, now let's get started. One more information, as I told you every time, please join our WhatsApp channel. The link of these notes and the PDF of these notes will be available in our WhatsApp channel. You can download. Questions will be putting in our WhatsApp channel. So this will be a major source. So please join this WhatsApp channel. The link of the WhatsApp channel is there in the description section of this video. So please go there and join as soon as possible. Okay, now let's get started. So as I already told you, there will be three parts for this chapter. Okay, part 1 and part 2 we have already completed. So if you haven't watched, the link of those videos will also be there. In part 2 we have already covered types of solutions and concentration terms and solubility. In part 1 we have completed this one. In part 2 we have completed vapor pressure and ideal and non-ideal solutions, and in part 3 we are going to cover today colligative properties, very important topic, and then abnormal molar mass. Okay, so if you haven't watched this part 1 and part 2, the link of these videos will be there in the description section. So please watch that and then come to this video. Okay, now let us go to the weightage year wise. So just let us see how many questions have been asked. So every time I have already discussed, you can easily expect 3 to 5 questions from this chapter. Okay, 3 to 5 questions from this chapter, and from this colligative property definitely you can expect 1 or 2 questions. Okay, so very important students, class today, please sit with your notebook and pen and write down every important formula and concepts that is going to be discussed today. Okay, so now solutions part 3, we have, as I told you, we are having colligative properties and abnormal molar mass. In colligative properties we are having 4 colligative properties. The first one, relative lowering of vapor pressure. Second one, elevation in boiling point. Third one, depression in freezing point, and the fourth one is osmosis. Okay, so we will be covering these 4 colligative properties, and then we'll go to abnormal molar mass. Okay, so yes, now let us first understand what is the meaning of this word colligative properties. Okay, colligative properties, what does that mean? So very simple thing, the properties of the solution which depend on the amount of solute added. Means, suppose I'll tell one property X is there. Okay, so there is a solution, sugar solution you have made. There is one property X. Okay, we don't know what is, just for understanding. Okay, so there's a property X of a sugar solution. Now this property will change based on how much sugar you are adding. Okay, then this property X will be called as a colligative property. Clear? So what I'm telling, those properties of a solution which depends on the amount of solute added is called as colligative property. I hope this definition is very clear. Nowhere this definition is asked in the exam, but yes, you should know the meaning of this term. Okay, now you can see this small one small cartoon diagram. What does it say? This is a solution, right? These are the number of solute particles. So the properties of these solutions, okay, will change based on how many solute particles you have added. Clear? So these type of properties are called as colligative properties. Okay, now moving towards our first colligative property, that is relative lowering of vapor pressure. Okay, now in the part 2 video we have already discussed what is vapor pressure, and we have also discussed when we add a solute the vapor pressure decreases. Okay, now there is something called as lowering of vapor pressure and another term relative lowering of vapor pressure. So now you see, I'll discuss this formula, but let us understand. You have a pure solvent, its vapor pressure is P0. Okay, we have a pure solvent. Okay, we have a pure solvent and its vapor pressure was P0. Now what we did, we added some solute to this. Okay, we had this pure solvent, Okay, apart from this, we added some solute in it. Okay, now this is a solution. Now the vapor pressure of this one I am denoting as P. Okay, so this is what? Solvent. Okay, and this is solution. Okay, so solution vapor pressure is P and solvent vapor pressure is P naught. Now can you tell me what mistake I have done in this diagram? Can you just think? I have told you many times in the part 2. Vapor pressure we can only observe in a closed container, right? Are these containers are closed? No, right? So this diagram is slightly mistaken. Let us correct it. We should close it. Okay. So now here are some vapor, that is P naught, and here are some vapor pressure, that is now P. Now P is the vapor pressure of the solution. We have already known that when we add a solute, the vapor pressure of the solution decreases. So definitely P will be less than P naught. Clear, very very clear. And the reason I have already explained. If you do not have understood, you have to go to that video and watch again. Okay. Now what happens? P naught is the pressure of the pure solvent and P is the pressure of the solution. Now what is the difference between these is called as delta P. What is the value of delta P? Change in the pressure. So that will be equal to P naught minus P. Okay. Now when you say relative lowering of vapor, this is lowering of vapor pressure. How much the vapor pressure has decreased. Now relative lowering of vapor pressure means with comparison to the initial pressure, how much it has decreased. So what we have to do? Simply we have to add P naught. Okay. So yes. Now when you compare the change in the vapor pressure with respect to the initial pressure, then we call it RLVP, that is relative lowering of vapor pressure. Now this is equal to what? This is equal to mole fraction of the solute. Now you see this property relative lowering of vapor pressure depends on mole fraction of the solute, or I can say depends on the amount of solute added, right? So that is why I can say that relative lowering of vapor pressure is a colligative property. Just remember the definition of colligative property, that it is a property which depends on the amount of solute added. So now this delta P by P naught is equal to XB. If XB will change, this term will also change. So it is directly depending on the mole fraction of the solute or the amount of solute. So that is why this is also a colligative property. Now NB, that is XB, can be represented as number of moles of B by number of moles of A plus number of moles of B, right? Now here a trick comes for dilute solutions. You know, all of you, what is dilute solution? Dilute solution means the solvent is very much in quantity, solute is very little in quantity. If that is there, then what happens? We can assume that for dilute solutions, NB is very very less than NA. Right? So in that case what will happen? We can ignore this NB. So now you can see delta P by P naught is equal to P naught minus P by P naught is equal to XB, and XB I am writing as NB by NA. Here I am not mentioning NB because I am assuming that NB is very less as compared to NA. And remember, this formula is what we need to use most of the times in the question so that our answers can be calculated easily. Okay. So I hope everything about RLVP is clear. First of all, when we add a solute to the solvent, the vapor pressure decreases. The decrease in the vapor pressure is called as lowering of vapor pressure. That is delta P. When you compare it with the initial pressure, that is delta P by P naught, this is called as relative lowering of vapor pressure, and it is equal to mole fraction of the solute. Because it is depending on the amount of solute added, we call this this property RLVP is a colligative property. For dilute solution, we have little modified formula. So now what is your task? Just write down this RLVP and write down these two formulas. Okay, note it down. Next, go to the question now. Now let us see how easily we are able to solve the question. Next one. The vapor pressure of water in the solution having 50 gram of urea dissolved in 850 gram of water is. Okay. So yes, now let us see. Whenever you read a question, just note down the data that is given. Vapor pressure of the water in the solution containing 50 gram of urea. So I have molar like mass of the solute. So I'll write W for that. Okay. W2, mass of the solute is 50 gram, and then dissolved in 850 gram of water. So mass of the solvent is 850 gram of water. Now vapor pressure of the pure water at 298 Kelvin. Okay, so pure water, I told you P naught, that is 223.8 mm Hg. Okay, you need to calculate the vapor pressure of the water in the solution. Okay, so now what happens, we have this formula, P naught minus P by P naught is equal to XB, and XB can be written as NB by NA. Right, now I'm not writing NA plus NB, okay, because I have ignored NB. I told you most of the time we need to use this formula for easy calculation. Now if P naught is 23.8, P I need to calculate, P naught is again 23.8, and NB, number of moles of solute, will be given mass by molar mass. So urea molar mass, you should remember, it is 60 gram per mole, so 50 by 60, right, given mass by molar mass. I'll write here N2 is equal to 50 by 60, and N1, that is number of moles of water, is 850 by 18, right, given mass by molar mass. Now if I solve this and I calculate, I'll get P is equal to 23.4 mm of Hg. Okay, so the answer for this question will be option number A. Now I'll tell you a very easy trick to solve this question, the concept, the logic that you need to use here. See here, I told you very first thing, when we add a solute, the vapor pressure will definitely decrease from the pure solvent, and now it is given that the pure solvent vapor pressure is 23.8. Pure water vapor pressure is 23.8. So when you add urea in it, the vapor pressure will definitely decrease. So in that case, what I can do is I can eliminate these two options. Option D I can eliminate, and option B I can eliminate, because these are more than 23.8, right? Now when we add a solute, the vapor pressure decreases, but not to very extent, okay, just a small decrease you can check. So now from 23.8, 12 is like almost half, right? So this much decrease does not take place, so that is why we can eliminate this option also. So just by looking at the options, we can say that answer is option number A, and you just need 2 seconds to solve this question, right? Okay, now let us solve the next question. Let us go to the next topic, that is second colligative property, elevation in boiling point. Okay, so here what is the concept? When a solute is added, okay, when a solute is added, the vapor pressure decreases, so the boiling point of the solution is greater than the pure solvent. So from the word elevation in boiling point, it is clear that when you add a solute, it becomes a solution now, and the boiling point of this solution will be more than the boiling point of the pure solvent. And now you see here I have written something about vapor pressure also. Now your question may arise, ma'am, what is the relation between vapor pressure and boiling point? Students, there is a very good connection between the vapor pressure and the boiling point. Okay, vapor pressure, boiling point are dependent. Let us see how. Okay, so now you should understand what is boiling point. Okay, what is boiling point? Boiling point is that temperature. Okay, remember, boiling point is that temperature where the vapor pressure of the liquid, okay, is equal to the atmospheric pressure. Atmospheric pressure. Clear? Any liquid is there, it will have some vapor pressure. When these vapor pressure is equal to the atmospheric pressure, that is 1 atm, then the liquid starts to boil, and that temperature at which these two things are equal is nothing but your boiling point. Now understood what is the relation between boiling point and vapor pressure? Okay, now let us understand one case here. See, so to boil any liquid, okay, to boil any liquid, what is the thing that you have to do? You have to make the vapor pressure of that liquid equal to the atmospheric pressure, right? To boil any liquid, to make any liquid boil, you have to make the vapor pressure of that liquid equal to the atmospheric pressure. Now let us take one example. Suppose we have a container here and we have water here, okay? So we have water here. Now for water, what happens, that this vapor pressure is 1 atm, okay, at what temperature? At 373 Kelvin, okay, or I can write as 100 degree Celsius. Okay, so at 100 degrees Celsius, okay, at 100 degrees Celsius, the vapor pressure of the pure water is 1 atm, and outside also it is 1 atm, right? So now these two are equal, and as a result of which the water boils at 100 degrees Celsius. Now what happens? Let us add some solute to it. Okay, let us add some solute to it now. Okay, now if I add some solute to it, what will happen? Okay, now let us see. Now when you add the solute, the vapor pressure will decrease. We have studied that when we add solute, the vapor pressure decreases. So now what will happen? At 100 degrees Celsius, the vapor pressure will not be 1 atm, it will be, let it be around 0.8 atm. Let it be, for just a example understanding. What I am saying earlier, when there was pure water, at 100 degrees Celsius, the vapor pressure was 1 atm, which was equal to the atmospheric pressure, 1 atm. So the water was starting to boil. But now what happened? You added some solute to it, and as we know, the vapor pressure decreases on adding solute. So now at 100 degrees Celsius, it cannot be 1 atm, it will be now 0.8 atm. But now this liquid will not boil. What you have to do? You have to give more heat so that more vapor pressure can be created, and it can match now 1 atm. So now what you did? You started heating it for more time. You started heating it. After some time, the pressure became here 1 atm. And at that time, the temperature had become 102 degrees Celsius. So now at 102 degrees Celsius, the pressure here is 1 atm, which is equal to the atmospheric pressure. Right? Now you see the liquid will start boiling, but at what temperature it is boiling? At 102 degrees Celsius. So there is what? There is an elevation in boiling point. The boiling point has increased, right? So this is the fundamental rule why vapor pressure affects the boiling point. Now where do we use it in our daily life? Can you give me one example, or think of an example for this? You might have seen that we boil eggs, right? We add some salt to that. So what happens that when we add some salt to it? When we add some salt to it, the boiling point of water increases, right? So water will be in the liquid state for more period of time. So the food will get time to be cooked. Okay, this is an example from our daily life. Okay, now you can see this graph here. Okay, see here. This graph is, this is the vapor pressure of the solvent, and this is the vapor pressure of the solution. As the temperature is increasing, the vapor pressure will also increase, right? When you increase the temperature, more vapor will create it, so vapor pressure will increase. And this is the atmospheric pressure. So for solvent, it touches this line at T0B, but for solution, it touches at TB, which is a higher temperature. So this is the vapor pressure of the pure solvent, this is the vapor pressure of the solution. Sorry, this is the boiling point of the pure solvent, this is the boiling point of the solution, and this gap is called as delta TB. Okay, now how to calculate this delta TB? That is what we can see here. So I will clear this area a little bit so that our formula is visible to all my students. Okay, now delta TB is equal to KB into M. What is M here? Molality. What is KB here? KB is your boiling elevation constant. Okay, now molality, you know the formula, given mass by molar mass into 1000 by mass of the solvent, right? So that is what is delta TB is equal to KB into M. Okay, I hope this formula is clear. I am not writing anything, just okay, let me mention here. KB is your boiling constant, okay, and M, small m, is your molality of the solute. Okay. Now your question may arise, ma'am, why is this a colligative property? Very simple answer. This property, which property? Elevation in boiling point, is directly proportional to the molality of the solute. Again, it depends on the amount of solute added. If you add more solute, there will be more elevation. If you add less solute, there will be less elevation, right? So this property is completely dependent on the molality of the solute. So that is why this is also a part of colligative property. Now let us quickly solve one question. Elevation in boiling point was 0.52 degrees Celsius. Okay, so delta TB I can, okay, one more thing I want to tell here. This delta TB, how can I represent delta TB? See, delta TB is equal to TB minus T0B. Okay, what is TB? Boiling point of the solution. You remember, solution boiling point will be higher. So that is TB minus T0B. So the solvent boiling point will be less. So TB minus T0B. Okay. Okay, now delta TB is equal to KB into m. According to the question, elevation in boiling point is 0.52. Then when 6 gram of a compound X was added and dissolved in 100 gram of water, the molecular weight of X is Kb is given to you 0.52 and molality given mass is 6 gram. Okay, molar mass I need to find out into 1000 by 100. Okay, so now what happens, if you solve this, you will be getting m as 60 grams. Molar mass unit is 60 gram per mole. So the correct answer for this question will be option number B. How easily we have solved this question, right? Similar type of questions are asked in your KCET examination also. Okay, now coming to the next one, that is freezing point. So now how we have explained that when you add a solution, when you make a solution, its boiling point increases than the boiling point of the solvent. But in freezing point, what happens, that is depression in freezing point. The third colligative property here is depression in freezing point. The depression means the freezing point decreases on adding a solute. Okay, so here the formula remains very similar to the first one, delta TF. So I'll correct this. This is delta TF is equal to KF into M, where M is again molality, KF is the freezing depression constant. Okay, now let us see, when a solute is added, the vapor pressure of the solution decreases, so the freezing point of the solution is lower than the pure solvent. Now again here question may arise, ma'am, what is the relation between vapor phase and freezing point? It is very similar to the relation between vapor phase and boiling point. So what is freezing point? See, freezing point is that temperature, okay, freezing point is that temperature when the vapor phase, okay, when the vapor phase of the solid, okay, vapor phase of the solid is equal to the vapor phase of the liquid. Okay, vapor phase of the solid will be equal to the vapor phase of the liquid. Now what happens here, let us understand this from the graph. See, this is a pure solvent. Okay, I'll take red ink. Okay, now this is the pure solvent, okay, this one, and it is the frozen solvent vapor phase. When these two are equal, the vapor phase of the solvent and the frozen vapor phase of the solid phase, when these two are equal, at this point the freezing point is reached. Okay, now you see, for this pure solvent and the frozen solvent, this is the point where these two are meeting, and the temperature here is T0 F, which is the freezing point of the solution, which is the freezing point of the solvent. Now what happens for solution? Why, the question you might be knowing, why the solution vapor phase is at the down? Because we know when we add solute, the vapor pressure decreases. So the solution vapor phase is this graph. Now when you extend it, it reaches the frozen solvent vapor phase at this place, right? So the temperature here is TF, which is lower than the T0 F, right? So what is my delta TF here? Okay, so what is the delta TF here? Delta TF will be equal to T0 F minus TF. Okay, now delta TF is equal to KF into M, where KF is your freezing depression constant and M is your molality. Okay, now let us solve a question here. The molality of a solution containing a certain solute if there is a freezing point depression of 0.184 degrees Celsius. Okay, very simple question. Delta TF is equal to KF into M. Okay, we need to calculate the delta TF is 0.184, okay, and KF is equal to 18.4 and M is the molality. Okay, now if I calculate the molality here, I'll get 0.01, right? So the correct answer for this question will be option number A. Clear? Very simple question. Similar questions are asked in your KCET exam. I'll show you the PYQs also, then you can check there. Okay, now coming to the fourth colligative property, that is osmotic pressure. For understanding osmotic pressure, first we need to understand osmosis. Okay, there's a lot of confusion in osmosis regarding different terms, so I'll make you very clear today to you. Okay, so let us draw. Let us go to a diagram. So we have a closed container. Okay, here I have partitioned it. This is a semi-permeable membrane. Okay, now this side I have solute, like solvent, water is there, and this side also I have water. Okay, Now what happens? I have added some solute in this side. Okay. Now what will happen? Which side the solvent will flow? Okay, that is what is osmosis you need to understand. The solvent will flow from high concentration of solvent to the low concentration of solvent. So see, here there is completely water molecules, here there is some water and some extra molecules of solute is there. So I can say that this is the high concentration of solvent, right, of solvent, like I'm telling in terms of solvent now. So the concentration is here, high concentration of solvent, right? So it will flow, the water will start flowing from here. Okay, this process is called as osmosis. Okay, the flow of solvent from its high concentration to low concentration is called as osmosis. Okay, now here there is a small change in the wordings. What I'll do, I'll say suppose there is no pure solvent, this side also I have some solute. Okay, both the side I have added solute. Then tell me which is the concentrated solution. Whenever we talk about concentration, it is with respect to solute always, right? So I'll tell that this is a highly concentrated solution and this is a low concentrated solution, right? So now what happens when we are expressing in terms of solute? Okay, you need to tell osmosis is the flow of solvent molecules from a region of low concentration of solute to a region of high concentration of solute. If you are telling in terms of solvent, then it is osmosis is the flow of solvent from the high concentration of solvent to the low concentration of solvent. Okay, so the point is wherever solvent is more, from that side to the side where solvent is less. Okay, I hope this is clear. Now what is osmotic pressure? So what happens is, suppose water is flowing like this, we want to stop it. Okay, so for stopping it, we need to give some pressure here. Okay, I have to give some pressure here so that the water will not flow this side. So this exact amount of pressure that I need to give to stop the flow of water from that side to this side, to stop osmosis, is called as osmotic pressure. Okay, now the formula for this is pi is equal to CRT. So this osmotic pressure is represented with the symbol pi. C is molarity, R is gas constant and T is temperature. So what is C here? C is molarity. Okay, and now what is R? R is your gas constant and its unit is 0.0821 or 0.083, okay, liter, atm, mole inverse and Kelvin inverse. Okay, so now that is there, and then we have molarity formula. We can explain given mass by molar mass into 1000 by volume of the solution in ml. Then you have R, gas constant, and T is your temperature. Okay, so this is how it is osmotic pressure. Okay, now we have something called as little more things to know about osmotic pressure, that if two solutions are there, solution A and solution B, and they have same osmotic pressure, then we have a special name for that, and that is called as isotonic solutions. Okay, please remember questions have been asked from here, that is why I have given you this term, that is isotonic solution. Now let us understand one more thing. I told you, see here, this side, okay, water was flowing from this side, I gave a pressure exactly to stop the flow of water from this side. Now what will happen if I give more force than just to stop, I'll give some more force. So now if I give more force than the osmotic pressure, then what will happen? Water will start flowing from this side now. I'm giving more force from this side. So what will happen now? If I give more force, the water will start flowing from this side. Okay. And now this is in the opposite direction of the original osmosis. So this is called as reverse osmosis. Okay, reverse osmosis. So that is what, let us see. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. That is, now the pure solvent flows out of the solution through the semi-permeable membrane. This phenomenon is called as reverse osmosis. Okay. Now let us understand where it is used. It is used very much in your desalination of water, or in the purifying of water, or I can say desalination of water. Okay, now what is this? Let us see. Now see, let us understand it in detail. Okay, so we have, again we'll do one diagram. We'll make a container, we'll divide it. So this side I have pure solvent. Okay, I have pure solvent this side. Next, this side I have some what I'll say, solute, or I'll say desalinated water. So I'll add salt here. Okay, now what happens? Originally, from which direction water will flow? Water will flow in this direction, osmosis, right? High concentration of solvent to low concentration of solvent. After that, what will happen? We can give a pressure from this side so that this water flow stops. Now what will happen? If I give more pressure, okay, more pressure, then what will happen? The water will start flowing in this direction. Water will start flowing from this direction. So what will happen? The salt particles will remain and water will flow. It is a semi-permeable membrane, so it allows only the solvent particles to move, not the solute particles. So what will happen? The pure water can be extracted from this side and can be collected on this side. So that is how desalination of water work, and this phenomenon is called as reverse osmosis. Okay. So yes, now coming to the one question here. Isotonic solutions have the same. So just now I have discussed that isotonic solutions have the same osmotic pressure. Okay, answer is option number C. Okay, now coming to the seventh and the last topic of this chapter, that is abnormal molar mass. Okay, now what is this abnormal molar mass? See, by using this colligative properties formula, what are we able to calculate? If any unknown solute is added, we can calculate its molar mass. Now let me take you an example and show you. Suppose I'll take elevation in boiling point. Okay. Now delta TB, if I write, is equal to KB into given mass by molar mass of the solute into 1000, okay, by mass of the solvent. I am writing M1. Okay. Okay, now what happens? By suppose we know all these data, then we can easily calculate M2, that is molar mass of the solute, without like if you know all these data, then we can calculate the molar mass of the solute accurately. Now what happens sometimes, in some cases, this molar mass calculation becomes wrong. What is the reason for this? The reason for this is association or dissociation of the solute particles. Now see, suppose you have dissolved NaCl in a solution. Okay, you have taken NaCl and you have dissolved it. Now what will happen? This NaCl, you are thinking that you have added only one particle of NaCl, but what happens when NaCl goes into water? It dissociates as Na plus and Cl minus. It forms two particles, right? So, and we have known that the colligative properties always depends on the number of particles formed. So, we are assuming that whatever property has come, that is because of one. But actually there are two particles now. So, in this way what happens? The calculation of molar mass becomes wrong. It becomes either more or less than the actual value. So, this is called as abnormal molar mass. Okay. So, you need to understand how can we correct this. So, this can be corrected by using a factor, that is Van 't Hoff factor. We will understand it in detail. So, for now you understand, whenever a solute either dissociates or associates, the calculation of molar mass becomes wrong. This wrong calculated molar mass is called as abnormal molar mass. It can be less or more than the actual molar mass. Now, suppose a problem is there, we need to find a solution. So, the solution or to overcome this problem is to use a factor called as Van 't Hoff factor. Okay. Now, what is Van 't Hoff factor? Okay. So, Van 't Hoff factor, I'll rub little bit this area so that we can see our formulas. Okay. So, what is Van 't Hoff factor now? So, we have three formulas for Van 't Hoff factor, but we are mostly using the third one. See, Van 't Hoff factor, first one is normal molar mass by abnormal molar mass, means the actual value, that is the correct value, divided by the wrong value. Okay. Next one is the observed colligative property by the calculated colligative property. Means how much is actual value, what is the observed value, and what is the calculated value. Okay, so calculated value will be wrong because we are not considering the Van 't Hoff factor. So the correct value divided by the wrong value. Now this is what is most important, and we have to use number of particles after dissociation or association divided by the total number of particles before dissociation or association. Okay, now for example, if I take NaCl and it is dissociating 100% to give you Na plus and Cl minus. So what is the Van 't Hoff factor for here? Number of particles after dissociation is 2 divided by number of particles before dissociation, that is 1. I will be equal to 2 by 1. Clear? Now suppose I have MgCl2. MgCl2 will dissociate as Mg2 plus 2Cl minus. So the Van 't Hoff factor here will be 3 by 1. So total 3 particles after dissociation, 1 particle before dissociation, 3 by 1. Clear? So okay. Now we will understand little more in detail. So now I told you that NaCl, if it is undergoing dissociation, Na plus and Cl minus, so the Van 't Hoff factor here will be 2 by 1, or I will say 2. Now I mentioned a word before also, this is correct if NaCl undergoes 100% dissociation. Okay, all the Na plus dissociates, then this formula is applicable. What if the degree of dissociation is not 100%? In that case we have this formula that for dissociation alpha, what is alpha here? Alpha is degree of dissociation. Okay, that is equal to I minus 1 by N minus 1. Now for association what happens? Alpha is equal to I minus 1 by N minus 1. Now what is this N? N is the number of particles. Like for example, for NaCl, N will be 2. If any dimerizes, like if I have like this CH3COOH, 2 molecules of CH3COOH forms CH3COOH whole 2. Okay, they become one molecule now. So earlier it was 2 molecule, now it became 1 molecule. So here it will be 1 by 2 association, 1 by 2 number of particles involved. Okay, so I minus 1 by 1 by 2 minus 1 will get. Okay, for association this formula, for dissociation this formula. You need to remember this formula. Okay, now what happens? Now how the modified formulas come for the colligative property? Very simple. First one is what? Relative lowering of vapor pressure. Relative lowering of vapor pressure, delta P by P naught, or I can write P naught by P by P naught is equal to I into XB. What is I here? Van 't Hoff factor. Now coming to second one, elevation in boiling point. Okay, I am writing EBP. So here if I remember, delta TB is equal to I into KB into M. Okay, next coming to depression in freezing point, that is delta TF. Delta TF is equal to I into KF into M. Okay, and the fourth one here, that is your osmotic pressure, pi is equal to I into C into R into T. Okay, ICRT. Clear? So these are the modified formulas that is how, if a solute is getting association or dissociation, then you need to use this formula. If it is 100% dissociation, then easily you can calculate I. If it is not 100% dissociation, then you have to use these two formulas and first calculate the I and then put in this formula. Okay, so yes, now let's solve question from here. So the Van 't Hoff factor for 0.1 molar barium nitrate solution is 2.74. The degree of dissociation is, okay, here it is degrees, means alpha is asked. So if you remember, alpha is equal to what? I minus 1 by N minus 1, right? Because it is dissociation. Now what is alpha value? We need to calculate. I value is 2.74. Now how will barium nitrate dissociate? Barium nitrate, how will it dissociate? It will give you barium 2 plus and 2NO3 minus. Okay, so total number of ions produced is 3 now. So what I can do here, 2.74 minus 1, okay, divided by 3 minus 1. So I'll get 1.74 by 2. Okay, So that is 0.87, and it is percentage, means if you multiply 100 we will get 87%. So the correct answer for this question will be option number B. Okay. So now we have learned the most important concepts. Now it is time to practice some questions. Okay. So these are your PYQs that have been asked in the previous years. Okay. So now this was the question that I gave you as a homework question in my previous lecture, right? So now I'll tell you the solution and you need to check whether you have got the correct answer or not. So let us read the question. Heptane and octane are given, right? So heptane is C7H16, right? Heptane, and octane is C8H18, right? So now these are heptane and octane, and their partial pressures are given, that is 105.2 kilopascal, and here it is 46.8 kilopascal. Okay, I'll also write the units, kilopascal and 46.8 kilopascal. And now they have also the masses given. So for heptane it is 26 gram and this one is your 35 gram. Okay, so now let us calculate the molar masses of this one. So this one molar mass is 100 gram per mole. So I'll tell you how you can calculate. So carbon is 7, so 12 into 7 first you have to take. 12 into 7, that is 84, 84 plus 16 hydrogen, right? So I'll get 6 plus 4, 10, 100 grams. Now here what I'll get, 12 into 8, right, that is 96, and then 96 plus 18. So I will get 114, right? So this molar mass is 114 gram per mole. Okay. Now let us calculate the number of moles of this one. So number of moles is what? Given mass by molar mass, right? And here the number of moles is given mass by molar mass. Okay. Now let us calculate the mole fraction. So mole fraction of heptane will be what? Number of moles of this one, that is 26 by 100 whole divided by 26 by 100 plus 35 by 114, right? And mole fraction of octane will be, so if I solve this, I'll get 0.456. Okay, so if I subtract 1 from this, I'll get 0.544, right? Now let us calculate the total pressure. Total pressure will be the partial pressure of this one, that is 105.2, okay, into mole fraction of this one. What is its mole fraction? 0.456 plus the partial pressure of this one, that is octane partial pressure 46.8, okay, and its mole fraction is 0.544. So if I solve this, I'll getting 73.43 kilopascal. Okay, so the correct answer for this question will be 73.43 kilopascal. So once again, very simple formula based question, direct question. So you have to check the answer and tell me whether you have got the correct answer or not. Okay, some PYQs. So yes, relative lowering of vapor pressure of a dilute solution of glucose dissolved in 1 kg of water is 0.002. The molality of the solution is, okay, please note down this question. This is very important question. Okay, very important question here. So now see, we know that relative lowering of vapor pressure has direct relation with mole fraction, but how can we calculate molality from that? So there is a very good relation, the formula relation between molality and mole fraction. So please note down this formula, okay, all of you. Yeah, molality will be equal to, okay, mole fraction of the solute, okay, divided by mole fraction of solvent, okay, into molar mass of solvent into 1000. Okay, so please note down this formula and then we'll start doing the question. Okay, now let us see. So the relative lowering of vapor pressure is given to you as 0.002. So if we know that delta P by P is equal to XB, right? So that means delta by P is 0.002. So XB is equal to 0.002. Then what is your XA, or that is of molar mass, or sorry, mole fraction of the solvent? So that will be 0.998, right? Yes, so we will get 0.998. Now the question has been asked to you that for 1 kg of water. Okay, so now if we solve this one, okay, now let us substitute these values. What is the, we have to calculate molality. Mole fraction of the solute is 0.002, mole fraction of the solvent is 0.998, right, into 1000, and by the molar mass of the solvent is 18. Water is the solvent, right? So molar mass of the solvent is 18. Now if you solve this, I'll get 0.111. So the correct answer for this question is option number C. So I'll label this question as hard. Okay, it is a hard question. Why? Because this formula every one of you might not be knowing. So this year it has been asked in the previous year, so it is now important to learn this formula. Okay. Okay, now coming to question number 2. The rise in the boiling point of a solution containing 1.8 gram of glucose in 100 gram of solvent is 0.1 degree Celsius. The molar elevation constant of the liquid is. Okay, so now again this question is very simple. Let us try. Rise in boiling point. So we know boiling point formula, delta TB is equal to KB into M, right? Now delta TB is how much? 0.1 degree Celsius. KB we need to calculate. Molality, given mass of the solute, that is 1.8 gram, by molar mass, that is 180, into 1000, right, by mass of the solvent 100, right? So now if I cancel these two, I'll get 18. I can cancel this one also, so I'll get 1 by 10. So I multiply this side, I'll get 1 is equal to KB. Okay, so it will be 1. So correct answer for this question is option number D. Okay, now very simple question. Let us move to the question number 3. A non-volatile solute A tetramerizes in water to the extent of 80%. 2.5 gram of A in 100 gram of water lowers the freezing point by 0.3 degrees Celsius. The molar mass of A is. So yes, this question is also very important from the Van 't Hoff factor. Freezing point, so you know the formula, delta TF is equal to I into KF into M. Now why I used I? Because you see something about tetramerization, extent of tetramerization, association, these all things are there, right? So we need to use Van 't Hoff factor here. Means the solute becomes is undergoing association, right? Okay. Now what do we need to calculate? I value, and I told you for this one, alpha for association is I minus 1 by 1 minus n by 1. So what is alpha value? We need to calculate. Alpha value is 80%, so I can write it as 0.8. I value I need to calculate I minus 1, and tetramerization means 1 minus 4 by 1, right? So now what I'll get? 0.8 is equal to I minus 1 by, so this will become 3 by 4. I can write it as 4 by 3, and then here a negative. So 0.8 will be equal to, so I'll multiply this 3 on this side. Okay, so I'll get 2.4. 2.4 will be equal to minus 4i, okay, and then plus 4, right? So now if I subtract this one on this side, so I'll get 2.6, right? I think that is, sorry, 1.6. Okay, 1.6 I'll get, minus 1.6 is equal to minus 4i. So I value will be 0.4. Clear? I value is 0.4. Now let us substitute that here, 0.4, and then KF value is 1.86, and M, molar mass 2.5 gram, given mass of the solute, by molar mass I need to calculate, into 1000, by mass of the solvent is 100 gram, right? So now if you solve this, and delta TF value is given to you as 0.3. Okay, now you solve this and calculate the M value. So if you solve this and calculate the M value, you will be getting around 62. Okay, so the correct answer for this question is your option number A. Okay, so please check this. This part calculation is little tricky one. You need to understand how to calculate it, and then some small calculation is involved. Okay, fine. Now let us go to the next one. Fourth question, which of the following colligative properties can provide molar mass of proteins, polymers and colloids? So this is, you have to remember, osmotic pressure is a colligative property which can be used to calculate the molar mass of the macromolecules. Okay, so the correct answer for this question is osmotic pressure, option number B. Now coming to question number 5. Which of the following solutions of the aqueous solution should have the highest boiling point? Okay, now see, these all are your what? Ionic solvent, you can see, ionic solutes. So delta TB formula is I into KB into M, right? Now if I Okay, you see molar, 1 mole, everyone is 1 mole, so we can say concentration is constant. Solvent, aqueous solution, so Kb is also constant because Kb value is for the solvent, right? Kf and Kv value is for the solvent. Now same solvent is used, that means Kb value will also be same. So delta Tb will directly depend on the I value. Wherever I is more, delta Tb will be more. Elevation in the boiling point will be more. So for this one, I is equal to 2. For this one, I is equal to 3 because 2 Na plus and 1 SO4. So if I write NaOH will dissociate as Na plus and OH minus. So I value is 2. Na2SO4. Na2SO4 will dissociate as 2 Na plus SO4 2 minus. Now NH4NO3 will dissociate as NH4NO3 will dissociate as NH4 plus and NO3 minus. Now KNO3 will dissociate as K plus and NO3 minus, right? So now what happens, if you see here, I value is equal to 2 and here I value is equal to 2. So where the I value is maximum? In option number B. If I value is maximum, then delta Tb will be more. If delta Tb will be more, Tb will also be more. So the correct answer for this question will be option number B. Okay. So yes, now this is as I give you every day a test yourself question. So please try to solve this question. If 3 gram of glucose is dissolved in 60 gram of water at 50 degrees Celsius, the osmotic pressure of the solution will be. Okay, so yes, you have to think little bit about this question and solve it. Okay, so students, that was the end of this video and the end of the first chapter, most important, very high weightage topic, that is solutions. We have covered all the topics that is required for your KCET 2025 chemistry examination. If you haven't understood any concept, if you have doubt in any question, please comment down, I will definitely address it. Okay, so I want everyone to make a formula sheet of this chapter, write down all the important formulas and keep it ready for your revision. Okay, so yes, now I can just request you that study every day with me so that you can make chemistry your strongest subject and you can score best in your KCET chemistry examination. Okay, so yes, now thank you for watching and please subscribe the channels for more such videos so that you do not miss out on a single episode of this series. And if you are liking it, please like and share also. And one more thing, all the very best for your KCET 2025 examination and please start working hard right now. Okay, thank you.